Hello, grade 12s. Welcome to our STEM in Action Boost series. And we're going to be looking at organic chemistry part 2. So in organic chemistry, we looked at part 1, and in part 1, we introduced the concept of organic molecules. And for part 2, we're going to be looking at classification of organic compounds. So you'd remember that we said that there are more than 9 million organic compounds. So just for it to be easier to name them, there is a way of classifying them into different classes or of families, and we classify them based on their functional group. So compounds that have got the same functional group are placed in one class because they perform pretty much the same type of reactions. They have got almost similar physical properties, so it is easy to classify them based on their functional groups. So if we look at our organic compounds, you notice that they are 1, 2, 3, 4, 5, 6, 7 classes that we are going to classify organic compounds into for your grade 12 level. Firstly are your hydrocarbons, your alkyl halides, your alcohols, your formals, your carbonyls, carboxylic acids, and your esters. So I'm going to start off with your hydrocarbons. So as the name suggests, hydrocarbon is a joining of two names, right? Hydrogen and carbon. So hydrocarbons are compounds that consist of only carbon and hydrogen. So they do not have those other substituent atoms besides just hydrogen. So there are three types of hydrocarbons. We have got alkanes, alkenes, and alkynes. And we also have got a general formula, right? So for alkanes, the general formula is CnH2n plus 2. And what you notice there is that the number of hydrogens is going to be double those of the carbons plus 2 extra hydrogens. And an example there is pentane. So pentane means that we have 5 carbons, and we have 1, 2, 3, 4, 5 carbons. And this is the structural formula, and this is the chemical formula. And next are our alkenes, and the general formula for alkenes is CnH2n. And what you notice is that we have removed the 2 extra hydrogens. So we get a compound like this one. So this is pent 2-in, and the 2 is identifying the position of the double bond. And we could either name it from the left-hand side, and it would then become 1, 2, or from the right-hand side, it would then become 1, 2, 3, but we choose the side that gives us the lowest number for our position. So we go with starting from the left-hand side. And thirdly, our alkynes, and the general formula is CnH2n minus 2. And as you can see, moving from alkanes to alkenes to alkynes, we are removing 2 hydrogens each time we move down. And an example that we get there is 2-pentyne, where the 2 is identifying the position of the triple bond. So moving from alkanes to alkenes to alkynes, we are removing a hydrogen each time, and we are moving from compounds that have only single bonds to ones where there is a double bond, and then one where there is a triple bond. So this is saturated, this is unsaturated, this is even more unsaturated. So as we are moving down, we are also increasing in unsaturation, or moving up, we'll be increasing in saturation. Our hydrocarbons, where do we usually find them? So you notice that with hydrocarbons, we start from, as we already indicated in part 1, we have got methane, ethane, propane, butane going onwards. And we also indicated that as we move up or down the series, as we increase the size of the compounds, their boiling points is going to be increasing. And the first 4 hydrocarbons are gases at room temperature. Then from carbon number 5 to about carbon number 16, they are liquids at room temperature. And from carbon number 17, those with 17 carbons onwards tend to be solid at room temperature. So you get your natural gas that we use for heating. And most of hydrocarbons, we indicated that they have a low boiling point because of their weak intermolecular forces, because they are nonpolar, right? So they are very flammable. They easily can be ignited into a flame. So they find uses as fuels. And here is natural gas that is used for home cooking. And we also use them for our to fuel things such as, this is a jet, and our petrols, our diesels for our vehicles. And for example, jet engine contains hydrocarbons with 8 carbons to about 16 carbons. It's a mix of various hydrocarbons from as small as 8 carbons to ones with 16 carbons. So most of hydrocarbons, they find their uses as fuels. So this is a secondary alkyl halide. And what you notice is that the carbon that is bonded to the halide is bonded to 2 other carbons. So in the primary alkyl halide, the carbon was bonded to one other carbon. Here it is now bonded to 2 other carbons. And also the number of hydrogens bonded to the carbon, they were 2 here. Now there's only one hydrogen bonded to that carbon. Then moving on to the tertiary. The tertiary carbon, we look at the carbon that is bonded to the halide, and you notice that this carbon is now bonded to 1, 2, 3 carbons. And it is not bonded to any hydrogen at all. So this is our tertiary alkyl halide. So moving from primary, secondary to tertiary, we are looking at the substituted carbon, right? The carbon bonded to the halide, and we are noticing that that carbon in primary alkyl halide is bonded to just one carbon and 2 hydrogens. The carbon here is bonded to 2 carbons. The carbon here is bonded to 1, 2, 3 carbons. And we can also look at it, like I said, in terms of hydrogens. And here we'll notice that the carbon is bonded to 2 hydrogens. Here it is bonded to 1 hydrogen, and here it is bonded to no hydrogen. So that's how we move from primary, secondary to tertiary. And most of our alkyl halides, they find uses in aerosols or refrigeration. Most of our fridges, they will contain an alkyl halide gas, although of late, because of their harmful toxic nature of the alkyl halides, they have since banned the use of alkyl halides in aerosols, because when they go out in the atmosphere, they were depleting the ozone layer, reacting with the ozone layer and all that. So they've put a ban on that. But traditionally, they had great uses in aerosols and refrigeration. The next up, we're going to look at alcohols. And alcohols contain the hydroxyl group or the hydroxyl functional group, which is the OH group. And this is the general formula. And what you notice is basically that we have got the general formula for an alkane whereby the H number of hydrogens for alkanes is C is H 2n plus 2, but this time we say 2n plus 1 and we replace the other hydrogen by an OH group. And then we've got our alcohols. And alcohols are again divided into three separate classes: the primary alcohols, secondary alcohols, and tertiary alcohols. And the difference, just as we find in the alkyl halides, is on the carbon that is bonded to the functional group. This is a methanol, which is the simplest alcohol. And what you notice is that the carbon that is bonded to our functional group, so all our functional groups are indicated in blue, and the carbon bonded to the functional group or the hydroxyl group is bonded to 3 hydrogens. For the primary alcohol, for the secondary alcohol, the carbon bonded to the hydroxyl group is bonded to 2 hydrogens. But at the same time, like I said, we can look at it in terms of carbons or in terms of hydrogen. So look at it in terms of carbons. This carbon is not bonded to any other carbon, right? The carbon that is bonded to our hydroxyl group. This carbon that is bonded to our hydroxyl group is bonded to 1 carbon. When we move to the tertiary, we'll notice that this carbon that is bonded to our hydroxyl group is bonded to 2 carbons. So moving from primary to secondary to tertiary, we are increasing the substitution of the carbon that is bonded to our functional group. So in the first one, the carbon is not bonded to any other carbon. In the second one, it's bonded to 1 carbon. In the third one, it's bonded to 2 carbons. And again, you can look at it in terms of hydrogens. In the first one, this carbon is bonded to 3 hydrogens. The second one is bonded to 2 hydrogens. And then lastly, only 1 hydrogen. So to decide which one is a primary, as you move from primary, secondary, tertiary, you can look at how many carbons is that carbon bonded to, or how many other hydrogens is it bonded to. And you can look at it in both ways and you won't get wrong. And our alcohols, like with other compounds, as you increase their size, you also increase their boiling point, because you increase the type of bonding that they can do, or the strength of the intermolecular forces. And alcohols, they also find use as fuels. So in some countries, they will combine alcohols with petrol, and it's called blended fuel. So it can also be used as fuels. And alcohols are also used as detergents because they are antiseptic. So most germs or bacteria, they can be killed if you apply an alcohol like ethanol. So they are also used as detergents. So what are some of the uses for our alcohols? Alcohols, they find uses as fuels, and because they are flammable. And I would also have you note, like we said, as you increase the size of the molecule, you get lower and lower boiling points. So the smaller alcohols are more flammable, and they're usually used as fuels. And also alcohols are also used as disinfectants because they have antiseptic properties. Most microorganisms or germs cannot survive in alcoholic environment. So if you swipe a table with an alcohol, you can disinfect the surface. We are going to move to our next class. In our next class, we have the carbonyl group. And carbonyl groups are divided into 2 types, right? We have got the formal carbonyls, and then we've got just the ordinary carbonyls. And the difference, as we shall note, with the formal carbonyls, the class that is under the formal carbonyls are the aldehydes, and the class that is under the ordinary carbonyls are the ketones. And the difference, as we shall notice, The carbonyl group is the CO group, the C double bond oxygen group. When the C double bond oxygen group here is found at the end of a chain, then we have got an formal or an aldehyde. When the CO double bond is found in the middle of the chain, whether it is on position 2 or whatever position it is, as long as the carbon that is bonded with oxygen is bonded to two other carbons on either of its side, then it is a ketone. When this carbon is at the end, then it is an aldehyde. So these are our carbonyls, and
Friends, we will now
our
sing
next
together
classification
hymn, the first
are
hymn,
carboxylic acids and
reflect
esters.
what a friend we
And
have in
carboxylic
Jesus, all our
acids,
sins and
their
griefs to
functional
bear.
group
What a privilege to carry
is the
everything
CO,
to God in prayer and all the
C
words.
double bond O, and then COH. So basically COOH, and that's the functional group for carboxylic acids. And for this one, it has got 1, 2, 3, 4, 5 carbons, so it's going to be pentanoic acid. And most of our acids, they are used in making manufacturing soaps, and they also are used in manufacturing esters, as we shall see. So this is the condensed chemical formula, and whenever you see that group there, C double bond OH, you will know that it's a carboxylic acid. That's an ester. And what you notice is that to make an ester, we are reacting a carboxylic acid and an alcohol. And in this case, this is the part with the carboxylic acid. So if we take this carboxylic acid with 5 carbons, 1, 2, 3, 4, 5 up to there, and then we join it up with an alcohol, we will form an ester. So some of the uses of carboxylic acids are basically to form esters. And with esters, you get various uses for esters, such as perfumes, food additives, and things like that. And in naming an ester, you have to identify the separation between the carboxylic side and the alcohol side. So in this case, this is the carboxylic side up to there, and this is the alcohol side from this oxygen to that side. And when we name them, we always start with the alcohol side. So the alcohol side here is a methyl group, and the carboxylic side is a pentyl. There are 5 carbons. So the name is going to be methyl pentanoate. So the pentanoate, the last part of the name, is coming from the carboxylic side of the ester. And the first part is coming from the alcohol side of the ester. And when you write the condensed formula, you will notice that the functional group appears as a COO in the middle of a chain. And again, it is separating the alcohol side to the right and the carboxylic side to the left. And when we name them, we always start with the alcohol side. In this case, it is a methyl. If there were 2 carbons there, it was going to be ethyl, 3 propyl, and then the last part comes from the carboxylic side of it. So here's a summary of the classification of organic compounds. We started off with hydrocarbons, and we said hydrocarbons, they consist of only carbon and hydrogen. Alkyl halides is where we substitute one of the hydrogens with a halide, and we get an alkyl halide. And we have alcohols where the substituent group is the OH group. Then we have got the formals where the functional group is the CO group. And we said that in a formal, the CO group is found at the end of the chain, whereas in a carbonyl, it is found in the middle of the chain. And then we have carboxylic acids where the functional group is the group COOH, and then we have esters, which is simply found when you react a carboxylic acid and an ester. And also, the further classification of hydrocarbons into alkanes, alkenes, and alkynes, and alkylides into primary, secondary, and tertiary, and also alcohols are also classified further into primary, secondary, and tertiary. And formals are the aldehydes, and the carbonyls are the ketones. Next, we are going to look at some of the reactions that organic compounds undergo. And there are basically 4 reactions that you have to know as grade 12s. And they are different type of reactions. So the first one is combustion reaction, substitution reaction, addition reaction, and then elimination reaction. So we'll start with combustion reaction. As the name suggests, combustion reaction is when you take usually it applies for hydrocarbons, is when you burn a hydrocarbon. And when you burn it, you are basically reacting with oxygen, and you always get carbon dioxide and water. And for this part, you are mostly asked to balance the equation. So you have to practice balancing equations. And like I indicated, it's usually easier to balance the equations if you start by balancing all the other atoms and you leave out the oxygen, and then you balance out the oxygen last after you've balanced the other ones. And our combustion reaction produces energy. And the energy is what we use in pretty much running most of the functions that we run in the world, right down from driving our cars. Most of our machines are providing energy for heating our materials and stuff like that. Then we have substitution reaction. And substitution reactions, they usually happen with saturated hydrocarbons. So remember we said that when we have a saturated hydrocarbon, we can say that it is full, right? Because the carbon is bonded to 4 atoms and we cannot add another atom. As opposed to an unsaturated where we have got a double bond and we have less number of atoms around the carbon and we can add another one. So substitution reactions occur for our saturated hydrocarbons because all we can do is replace an atom that is already there, or a substituting atom that is already there. So you get a reaction like this one where we have got a methane, and in this case we are reacting it with a chlorine molecule, and we get a product where we have substituted or replaced this hydrogen with a chlorine atom. And our other side product is going to be the remaining chlorine atom and the removed hydrogen. So in substitution reactions, you always have another product in addition to your main product. Then you have addition type of reactions, and addition reactions, they happen to unsaturated hydrocarbons. So with unsaturated hydrocarbons, like I said, you can regard them as unfull, so you can fill them up, right? So we have got this carbon, and this carbon, it has got 4 bonds around itself, which is fine, but it has got 4 atoms around itself, 1, 2, 3. So it means you can add another atom, then you remove the double bond. And such reactions are called addition reactions. So in this case, we are adding a hydrogen that is bonded to an X, where X can be any, can represent either an atom of a group of atoms, as we shall see. And what simply happens is that you add them across the double bond. So this hydrogen goes to one carbon, the other X goes to the other carbon. And we are going to look at some preferences that happen with such reactions. But the difference between the substitution and the addition, one of the differences is that in addition, we do not have a side product because we are simply adding to the molecule. Whereas in substitution, you are going to get another side product or a byproduct of the reaction. So whenever you see a reaction with more than one product, you can think in your mind it's probably not going to be an addition type of reaction. Elimination reaction happens to saturated hydrocarbons, whereby we remove, so to eliminate is to remove something. So we remove an atom from a saturated hydrocarbon, and we end up with a double bond or an unsaturated molecule. So here we're moving from an ethane, where all the carbons have got 4 atoms around themselves, and we remove these 2 atoms, that one and that one, and we form a double bond. So we're moving from a saturated hydrocarbon to an unsaturated hydrocarbon with a double bond. And we have a byproduct, which is the two hydrogens that we have removed in this case. So moving on, we are going to look further into addition and elimination, and more examples of that. So with the addition reactions, firstly, you have got hydrogenation, which, as the name suggests, hydrogenation comes from the word hydrogen. So we're adding a hydrogen or a hydrogen molecule. Then you have got hydrohalogenation. And as the name suggests, you have got a hydrogen, and you've got a halogen. So it is a compound that is consisted of a hydrogen and a halogen, such as hydrochloric acid, HCl, right? Then you've got halogenation, whereby you are adding a halogen molecule, where both atoms are halogen molecules. And then hydration is whereby you are adding water. As the name suggests, hydration, hydra means water, right? So firstly, I'll mention that addition, I'll reiterate that addition reactions are done or performed on unsaturated hydrocarbons, where we can add other atoms to the compounds. So this is the first one. This is a pentene with 3 carbons, and hydrogenation, we are adding this hydrogen and we get a saturated pentane, and we apply some of the conditions. There has to be heat, and we also use the catalyst to speed up the reaction, and the catalyst that we use are platinum or palladium. And you have to know the type of reaction, and you also have to know the conditions. So most of the questions that you get might ask you to identify the reaction conditions, or they'll give you your starting reactant, and they'll give you what we are adding, and then they'll ask you to identify the product that you're going to form. So be able, or you might be given this product, and you'll be asked to identify what the starting reagent was. So be able to move both from your reactants to the products, or from the products back to the reactants, and also be able to identify the reaction conditions for each of these reactions. Hydrohalogenation, like I said, we are adding a hydrogen that is bonded to a halogen, and the halogen can either be fluorine, chlorine, bromine, or iodine. And the reaction conditions are that the solvent must be inert. So an inert solvent is simply a solvent that does not react, that is not reactive. So you remember that in our periodic table, we identify the elements in group 8 as inert elements because they do not react. So a solvent that you use should be a solvent that is not reactive. And usually what is usually used there is chloroform, or we make sure that there's no water, right? Because if there is water, the water is going to interfere with the reaction. Or if we have got a solvent that is not inert, it's going to interfere with the reaction, and we produce a different product than the one that we want. So in this one, we are adding the hydrohalogen across the double bond, and what happens is that the hydrogen goes to this carbon, then the chlorine or halogen goes to the other carbon. And I'll mention here that we could have added the hydrogen to this carbon and the chlorine to that carbon. But you have to know that there is a preference with this type of reaction. So when you do this reaction, the halogen is usually added to the more substituted carbon, and that is usually the central carbon. Or it is added to the carbon that has the least number of hydrogens, or that is bonded to the most number of other carbons. So if you compare this carbon and that carbon, you notice that this carbon is not bonded to any other carbon, but this carbon is bonded to 2 carbons. So the halogen is going to be added to the carbon that is bonded to the most number of carbons, which in this case is that carbon. Or you can say it's going to be added to the carbon that is bonded to the least number of hydrogens. Or you can say it's going to be added to the most substituted carbon. So this is a halogenation. Like we said, you are adding a halogen, and your halogen can either be a fluorine, chlorine, bromine, or iodine. And again, our solvent should be net, and they should not be water. Those are the reaction conditions. And again, for this one, it doesn't matter where we add them, because remember it's a diatomic molecule, so they are two similar atoms. So we can add either one to either of the two carbons that are part of the double bond. So we add one there, another one there. For this one, it doesn't really matter. Hydration is where we're adding water, and we use a catalyst. And our catalyst is usually an acidic solution or an acidic environment. And usually we use phosphoric acid, but any acidic medium can also act as a catalyst for this reaction. And heat is usually applied for this reaction, but it's not an important factor, a part of the reaction. And again, for the hydration, that preference applies, where in this case we are adding the OH to one of the carbons and adding the hydrogen to the other carbon. And we add the OH to the most substituted carbon, right? Just like we indicated with hydrogenation. So with the option of adding here or there, we are going to add our OH to this carbon because it is the carbon that is surrounded by the most number of other carbons, or the carbon that is the least number of hydrogens. That is the one which is preferred to add the OH group. And what you produce is an alcohol, right, with the hydroxy group, functional group. So we're going to look at substitution reactions. The first one is going to be halogenation of alkanes. So here we've got a reaction of ethene reacting with bromine. And this reaction is done under UV light. So you've got those three steps: initiation, propagation, and termination. And in this case, we are simply substituting our hydrogen with a Br, and we also get a byproduct, which is going to be HBr. We can also do halogenation of alcohols, whereby we react an alcohol with a hydrohalide. And what simply happens is that we substitute the alcohol group or the OH group by the halide group. So we get a product which is a haloalkane, whereby we've replaced the alcohol group with a halogen, and we also get a byproduct which is water. And we can also have a substitution reaction, which is a hydrolysis reaction. And what you notice here is that it is almost the reverse of the previous reaction, whereby we are starting with a haloalkane. So we have got our functional group of a halogen, and the chlorine here represents a halogen group. It can be a fluorine, chlorine, a bromine, or an iodine. And we are reacting with the water. And what happens here is that we substitute the halide group with an alcohol group or OH group here, and we get a byproduct which is simply the removed or substituted halide combining with the remaining hydrogen from the water to be one of our byproducts. So we're going to look at elimination reactions, and there are three types of elimination reactions that you have to know. The first one is dehydrohalogenation, dehydration, and then cracking reactions. So this is an example of a dehydrohalogenation reaction. And as the name suggests, hydrohalogenation, remember, in the addition reactions, we had a hydrohalogenation reaction where we're adding a hydrogen and a halogen. In this case, we are removing a hydrogen and a halogen. So in this case, and for elimination reactions, like I said, they are performed on saturated compounds, and we end up with an unsaturated compound, or a compound that is a double bond. So in this case, we are removing this halogen and that hydrogen, and they have to be bonded to adjacent carbons or carbons next to each other, such that we can form a double bond between those two carbons. And for this reaction, we use sodium hydroxide or any base, and we also apply ethanol and some heat, and we get that product, which is a double bond, and we have got two other byproducts, which is sodium chloride and water. And I want you to notice that this is our base, so the sodium is going to get bonded to the chlorine, and then the OH in the sodium hydroxide is going to be bonded to the hydrogen to form water. So if you have a different base, let's say you have got a base such as potassium hydroxide, it means that this product is going to become potassium chloride, and then this is also going to be water. And notice also that the halogen can be any of the halogens. It can be bromine, it can be chlorine, it can be iodine or fluorine. Then dehydration is where we are removing water, so we are reversing a hydration reaction, and we are removing OH plus a hydrogen, which are bonded to two carbons next to each other, and we are forming double bond. And the water that we remove comes out as one of the products. And the reaction conditions, we need an acidic environment, and there's also heating involved. The next is cracking. So cracking is a type of reaction where we take a large molecule that might not be of much use, and then we heat it, and we produce smaller molecules, and at times it will be more than one smaller molecules that are more useful than the one we started with. And there are two types of cracking reactions. One is where we just apply heat, and another one is a catalytic one where we use a catalyst, and one of the catalysts that is used is usually palladium. And what you notice there is that we are starting here with a large molecule that has got 10 carbons, and we're ending up with, in this case, 3 separate molecules, which are smaller than the one we started with. And in this case, we have got an alkane, and these two are alkenes. And you can be asked to balance off a cracking reaction, and you have to make sure that the carbons you started with are adding up. So here we started with 10 carbons, and are adding up with 4 plus 4, which is 8 plus 2, which is 10. So when you are balancing it, make sure that you balance it such that your number of carbons are equal from both sides. So that's a cracking type of reaction. Then I'm going to explain further that preference of product that I talked about. So when you do a reaction such as this one, remember we said that this is a hydration reaction. We are adding water, and we have the option of adding the OH to that carbon or that carbon. And what you notice is that there is preference for the OH to be added to the more substituted carbon, or the carbon that is bonded to more number of carbons, and it is this one. So when we add them, we are going to get, we can either add it there or we add it there, but this is our major product, meaning to say that when you do this reaction, you are going to form more of this product than that product, which is our minor product. So if you do this reaction, you are going to produce a mixture of products. And maybe you get 70% of your products are going to be your major product, and maybe just 30% are going to be your minor product. And there are processes that can be applied to further separate them so that you have got just this one and that one in separate, to separate our products. Now we're going to look at polymerization. So before we look at polymerization, we're going to define the term macromolecules. So macromolecules are molecules that consist of a large number of atoms. So we know that we have got small molecules. We identified methane as one of the simplest molecules that you get. But it is possible to react small molecules, and you keep reacting them, adding smaller and smaller molecules until you get a very large molecule. And once we get a large molecule, we describe it or we identify it as a macromolecule. So a macromolecule is simply a large molecule that consists of a large number of atoms. And a monomer is a small organic molecule that can be covalently bonded to each other in a repeating pattern. So it means that there are some molecules whereby you start with one molecule and you can link it up to the next molecule, to the next molecule, until you form a chain of such molecules. And the single molecule that you are starting with is what we call a monomer. And when you join them up to form many monomers joined together, then we have a polymer. Right? So mono means one and poly means many. So you can combine those two words and you notice that monomer is simply that single molecule and polymer are the many molecules that have been joined together by a covalent bond. So a polymer is a large molecule composed of small monomer units covalently bonded to each other in a repeating pattern. So here we have got a monomer, which is an ethene molecule. And when we polymerize it, we are going to get a chain of ethene molecules. And the N here represents the number of monomers of ethene that we have. And when you put the N here, it represents the number of repeat units of ethene that we are going to be having in our polymer. So what you notice here is that this is the repeating unit, right? So the CC bond, that's the repeat unit, is repeating itself here, repeating itself here, and repeating itself here again. So when you are given the structure of a polymer, you should be able to identify which unit is repeating itself in that polymer. And that repeat unit will give you what the starting monomer was. So a monomer is simply a small organic molecule that can be covalently bonded to each other in a repeat pattern. We're going to focus more firstly on addition polymerization. So addition polymerization is a reaction in which small molecules join to form very large molecules by adding on a double bond. So with addition polymerization, we are starting with a monomer that is an unsaturated monomer, or that is a double bond. And what we are simply doing is we are adding another molecule that also has a double bond to the double bond. Because remember we said that if we have got an unsaturated molecule, right, with a double bond, it is possible to add atoms to that double bond. So in this case, we are not adding an atom, we're actually adding another molecule, like itself. And that's basically how you get addition polymerization. So an addition polymer simply then becomes a polymer formed when monomers, usually containing a double bond, combine through an addition reaction. So here's an example of an addition polymerization, which we already talked about, where we have got an ethene molecule, and we polymerize it to get a polyethene. And again, like I said, be able to identify the repeat unit, which is this part, and that part. And the second one, what we have simply done here is we have substituted the hydrogen here with a methyl group. All right? So it is possible to get different types of polymers depending on the atoms that you have on your monomer. So here we can substitute this hydrogen by a methyl group, like what we did here. We can substitute it by a halogen compound. We can substitute it by halogen group, and each time we'll be getting a different type of polymer with different properties. So depending on the properties that we want or the type of polymer that we want, we can substitute the groups on a monomer to get different types of polymers. So for this one, we are starting with a propene monomer. And when we polymerize it by adding to the double bond, we are going to get this polypropylene, and that is the polymer. And again, be able to identify your repeat unit, the blue, the black, and the blue again. And like I said, the N represents the number of monomers we are starting with, and here the N we put it as a suffix to represent the number of repeat units that we have produced. And like I've said, here we're just going to practice identifying the repeat unit if you're given a polymer. So if you're given the structure of a polymer, you should be able to figure out what the starting monomer was. So in this case, we have already done that. So this is going to be a repeat unit. For this one, where we have substituted that part with a halogen, and this is going to be our repeat unit, right? So it's repeating itself here, here, and there again. Or we can have this one, which looks a bit more complicated. But again, what we have simply done here is we have replaced that position. So firstly, with the methyl group, with the halide group, now we have got this group here, which is actually and our third example is this one, which looks a bit complicated. But what we have simply done is we have replaced or substituted the methyl group here with the halide group there. And this time we have substituted it with actually an ester link, right? So that's an ester link, and we have already talked about that ester link. So this is actually an ester group that has been attached to our ethene monomer. And we can polymerize that by adding to this double bond, and we are going to get this as our repeat unit. So that's the repeat unit repeating itself in blue, black, as indicated by this difference in color. So again, be able to identify what the repeat unit is in a polymer. Then there is condensation polymerization, which is a different type of polymerization from the addition polymerization. And with this one, it involves molecules of two monomers with different functional groups which undergo condensation reactions with the loss of small molecules, usually water. And therefore, a condensation polymer is a polymer formed by monomers with two functional groups that are linked together in a condensation reaction in which a small molecule, usually water, is lost. So, in addition polymerization, we do not have a byproduct. We only start with our monomer, then we form our polymer. So there's no other byproduct. But here we are being told that with condensation polymerization, there is a byproduct, usually water. So here is an example. We said that we'll be having molecules or monomers with different functional groups. So in this case, we have got a carboxylic acid and an alcohol. And this is the functional group for the carboxylic acid, and this is the functional group for the alcohol. And one thing I would say also is that with condensation polymerization, the monomers that you add will usually or almost always have two functional groups of the same kind, right? Or one on one end and one on the other end, so that they can react on one end to add another molecule to the other side, or they can react on the other end to add another molecule to the other side. So both of them will have that. So in this case, this is our first carboxylic acid, and we can see that it has got a carboxylic acid group to its left and a carboxylic acid group to its right. And this R here simply represents a CH arrangement. So it can be, you can have 4 carbons there, you can have a ring structure there, you can have different number of carbons lined up, which is simply is the CH bond. And on the alcohol as well, the R simply represents a hydrocarbon chain, right? So it can be 2 carbons, it can be 4 carbons in that chain, right? So the R represents simply different lengths of chains in that molecule. But to note, like I've said, is that both of these monomers have got double functional groups on one end, such that you can react this part. So this carboxylic acid can react on its functional group to the right, can react with the alcohol, and we produce our water, right, by removing the OH from the carboxylic acid and the H from the alcohol, and we produce our water. That's our byproduct. And this alcohol can also react on the other side or its other functional group, likewise to link another or to join another carboxylic acid to its right. And again, we do that, and this carboxylic acid has got this functional group that has now reacted to this alcohol, and it also has got another functional group to its right, which can react to another alcohol. And we can keep adding them and adding them like that. So we can add another carboxylic acid here, or we can add another alcohol there. And what we produce is a polyester, right? Because this link here that we have is an ester linkage. So it's an ester because we are reacting carboxylic acid and an alcohol, so we know that we form an ester, and we call this an ester linkage, and the type of polymer we get, we call it a polyester. And we can have as many number of repeat units as possible. And in this case, our repeat unit will include the carboxylic group and alcohol group. So this is going to be what is repeating itself. Here we have got that first repeat unit, the second repeat unit, and we are going to keep adding both to the right and also to the left. So this is our carboxylic. So this is our ester linkage. That's the linkage that we produce from that reaction, another linkage from that reaction, and that linkage as well. So this is simply the addition reaction of polyethylene, starting from ethene to polyethylene, and we're now looking at some of the applications of addition polymerization. So industrial applications. So when we form polymers, most of the polymers that we form are so displayed here is again an addition reaction that we have looked at already. But now we're going to look at some of the industrial applications of this polymerization reaction. So most water bottles are formed from polyethylene, plastic grocery bags, polyethylene, plastic film, industrial installations, and toys, right? So most of the plastic material that we get comes from polymers, right? And in this case, polyethylene can produce these different types of industrial products. And they are, as you can see, they will have different properties in terms of how hard they are. So if you vary the formation process, you can get different products with different levels of hardness or softness, right, for different industrial applications. So polyethylene can be recycled and used again after reducing it to pellets and molding it into new shapes. So if you have got, this is waste material of polyethylene material, so you can, if people collect such waste bottles that we would otherwise throw away, and you collect them, and you can remold them into pellets, right? So you usually, they take them through a furnace, they melt them, and once they melt them, they then reduce them to these pellets, and they can remold them to form another product, which is recycled. So this is one way of reducing pollution or land pollution, by collecting waste bottles, and we can recycle them in that fashion. So I'm going to do some applications, and our first question is going to come from a March 2018 paper in question number 2. So if we look at this question, the first one, we have got a table that has got different compounds, and it says that the letters A to E in the table represent 6 organic compounds. There are actually 5. All right. So just by looking at these organic compounds, we are just going to identify a few things. So for A, we can identify a hydroxyl group, so it's an alcohol. For B, we can identify a formal group, which is making it an aldehyde. And obviously, this is an alcohol with the ol part. This is an ketone with the on part. and this is an alcohol again, right? That's the main functional group there. All right, so 2.1 says, write down the letter that represents each of the following. A tertiary alcohol, right? So we said that a tertiary alcohol, the carbon that is bonded to the hydroxyl group is going to be bonded to 3 other carbons, right? Or it is not going to be bonded to any hydrogen atom. So looking at our alcohols, we start with this one, right? And you notice that this one is bonded to 1, 2, 3 carbons. And another alcohol that we have is this one, and it's bonded to 1, 2. So this is our tertiary alcohol. So A is our tertiary alcohol. B, aldehyde, we have already identified compound B as our aldehyde. So compound B is our aldehyde. Ketone, we already said this is our ketone. We are given the chemical name, and when you have got on, it's a ketone. So compound D is our ketone. The functional isomer of compound B, so this is compound B, and you'd remember that we said the CO bond can either be at the end of the chain and you get an aldehyde, or it can be in the middle of the chain and you get a ketone. So the functional group for this compound is going to be a ketone, and our ketone is going to be D, right? So but means that there are 4 carbons, and here there are 1, 2, 3, 4 carbons. So these 2 are going to be functional isomers. But we can try to prove that. So I'm going to draw the structure for butane 2-on. It's but, so it means we have 4 carbons. So I'm going to go 1, 2, 3, 4. The on is on position number 2, so it means that the functional group, or the CO double bond, is on position number 2. We'll put it in position number 2. Then we fill in the rest of the spaces with hydrogens, making sure that every carbon has got 4 bonds around itself. This carbon already has 4 bonds, so we don't add the hydrogen there. We add 1 there, 1 there, and we're going to count. So this is the structural formula. We're going to come up with the chemical formula. So carbons, how many carbons do we have? 1, 2, 3, 4. 4 carbons. How many hydrogens do we have? 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens. And oxygens, just 1 oxygen. Then we count this one. How many carbons? 1, 2, 3, 4. 4 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens and 1 oxygen. So these 2 have the same chemical formula, but they have different structural formulas, and they are isomers to each other. So the functional isomer of compound B is going to be D. 2.2. Write down the IUPAC name for compound B. So this is compound B. It's an aldehyde. And aldehydes, they end with the name now, right? And we count the number of carbons. There are 1, 2, 3, 4 carbons, so it's a but. So the name becomes buta now, right? So this ending indicates that it is an aldehyde. Question 2.2.2, the IUPAC name for compound E. So firstly, we have to identify our functional group, and we already identified the OH group, or our hydroxy group, as a functional group. Then we need to identify the longest chain. And to identify the longest chain, let's start from this side. We are going to say 1, 2, 3, 4, 5, 6, 7. So this one will have 7. 1, 2, 3, 4, 5, 6, 7. This will have 7. 1, 2, 3, 4, 5, 6, 7. That will have 7 as well. But there's another longer chain, perhaps 1, 2, 3, 4, 5, 6, 7, 8. So this is our longest chain. So that's the one that we are going to use. So 8 means that we are dealing with an oct. Then we have to identify the position of our functional group, which is our OH. And we already said that this is the longest chain we are using. So if we start from this side, we are going to say 1, 2, 3, 4, 5, 6, and the position is going to be position 6. If we start from this side, it's going to be 1, 2, 3, right? So starting from the right is going to give our functional group the lowest possible position. So it means that we are going to start from that side. So it means that our OH is on position number, our alcohol is on position number 3. Then once we do that, we can come up with the parent name for our chain. So it's going to be octane 3O. It's an octanol, right? And this is the position of our alcohol. Once we have done that, we need to identify other substituents that are part of that chain, right? So this is our parent chain or our main chain, and we have got this group there, and it's on position 1, 2, 3, 4, 5, 6. So we have got on position 6, we have a methyl group. 1, 2, 3, 4, 5, 6. On position 6, we also have another methyl group. Then on position 1, 2, 3, 4, 5, we have N. So that's the other methyl group. On position 5, we have a ethyl group. So now we need to join all our substituents that are attached to our parent chain. And what you notice is that these two are the same, so we're just going to call it dimethyl. But we need to decide whether we are starting with ethyl or we are starting with methyl. And we ignore the di part, so we are only interested in that E and that M, and we use the alphabetical order. So E comes before M, so it means that we're going to start with the ethyl part. So it means that our name becomes 5 ethyl 6.6 because there are two of them, dimethyl, then the parent name, octane 3O, and there is no gap here. But another way we can write this is by saying 5 ethyl 6.6 dimethyl 3 octanol. So we can either put the 3 in front of the N and the O, or between the N and the O, or you can put the 3 before the octanol part, and both names will be acceptable for the naming of compound E. So that's our compound E. 2.3 says define define position isomers, and we already talked about position isomers. We said that these are compounds with the same structural formula but different positions of the side substituent. Then 2.4 says write down the structural formula of a position isomer of compound C. So we go to C. That's our compound C. Firstly, it's an alcohol because it has got that suffix O, and it's a but, so it has 4 carbons. So we're going to write 1, 2, 3, 4 carbons. Our alcohol is on position number 1, so it's going to be there. And we fill up the rest of the spaces with hydrogens, making sure that every carbon has 4 bonds around itself. So this is this compound, compound C. And we said that a position isomer is simply an isomer whereby the position of the substituent group is on a different position. So here's on position 1. If we draw the same structure and we put this OH on a different position, this will be an isomer of that one. And just realize that we are putting hydrogens. And these two are going to have the same chemical formula, which is going to be C4 H 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10. Oh, both of them are going to have the same chemical formula, but our position here is on a position 1 and there is on a position 2. So they are position isomers of each other. Then question 2.3, positional isomers. So we looked at positional isomers in organic chemistry part 1, and we said that positional isomers are isomers with the same chemical formula but different structural formula, right? And for position isomers, the substituent group is attached to a different position. All right. 2.4.2 says write down the structural formula of compound D. So this is compound D. We already wrote the structural formula. We're just going to go through it again fast. So firstly, we have to identify the chain, right? The parent name is a but. So there are 4 carbons. And it's an on, and that is a suffix for a ketone. And the position for the ketone group is position 2, so we're going to put it there. And you can also put it there, it will still be the same thing. And then we fill in the rest of the spaces with the hydrogen atoms. 2.4.3, it says write down the structural formula of the organic acid that will react with compound C to form a butyl propanoate. So the name is butyl propanoate. And we said that this part comes from the alcohol and that part comes from the carboxylic acid. So they want the structural formula of the organic acid that will react with compound C to form this one, right? So we want the structure of the acid. And propane means that there are 3 carbons. It's a carboxylic acid. So we convert the last carbon into a carboxylic group. Then we fill in the rest of the spaces with hydrogen. So this becomes the propanoic acid, which is the acid that will react with butanol, compound C, to produce butyl propanoate. So this is the end of our first application questions.